In the second segment, uh, I have just presented in this slide some physical techniques in determining the structure. And I have grouped it in such a way that whether it is a gas, or a liquid, or a solution, or a solid, what is the information that you will be looking for, and what kind of a spectroscopy technique or associated technique one can use it to understand the structure. If you want to do fingerprinting, you know, for example, if you want to do the fingerprinting of a gas, you can make use of IR spectroscopy and microwave spectroscopy, mass spectrometry, UV visible spectroscopy that every one of us know, and ultraviolet photoelectron spectroscopy that is called as a UPS, ultraviolet photoelectron spectroscopy. If it is going to be a liquid or a solution, then for fingerprinting, we make use of infrared, Raman, NMR, that is nuclear magnetic resonance, mass spectrometry, and UV visible spectroscopy. If it is going to be a solid, then for fingerprinting purposes, we use infrared, Raman, and powder X-ray diffraction. Powder X-ray diffraction is not a spectroscopy, but I have just included that because that is becoming an indispensable tool nowadays to characterize the solids. Okay, for fingerprinting and characterizing the solid. So, for completion's sake, that is also a structure determining technique, and therefore I have included there. So mass spectrometry you can use if it is a solid for fingerprinting, and UV visible spectrometry, spectroscopy, you can use it for solids. And for solids, when you use UV visible spectroscopy, for liquids, gases, you can use it in the absorption mode. But for solids, we use it in the reflectance mode. Okay, so what are the groups present in my molecule or in my compound? If it is in the gaseous phase, I make use of infrared spectroscopy, mass spectrometry, and nuclear magnetic resonance, NMR. If it is a liquid or a solution, similarly, I use IR, Raman, mass, and NMR. Okay. If it is going to be a solid, then I'm going to use IR, Raman, mass spectrometry, NMR. Solid state NMR also can be done. That is called as a magic angle spinning NMR, MAS, magic angle spinning NMR. And then Mossbauer spectroscopy. Of late, this spectroscopy technique is almost dying in our country. People are not extensively using it. Earlier, people used to use it extensively. This is a very, very quite useful technique which people are not using it regularly. And for molecular symmetry, in order to find out what is the molecular symmetry that is present in a molecule, so we again take the help of infrared, microwave spectroscopy can be done, and electron diffraction. Electron diffraction is not a spectroscopy, it is a diffraction. But for the sake of completion, so I have circled all those things which are essentially, other than the UPS and EXAFs, which are not actually exactly used as a spectroscopy. They are for the sake of completion, as I told you before, I have added it. Okay, molecular symmetry can be found by electron diffraction. And liquid or solution, IR, Raman, NMR. And if it is a solid, I would prefer IR, Raman, NMR, NQR. That's a very, very important technique, nuclear quadrupole resonance spectroscopy, and single crystal X-ray diffraction. That's a diffraction, that is not a spectroscopy technique. But what is this nuclear quadrupole resonance technique? That means if you are having magnetic ions in your compound, and if you want to know whether these magnetic ions or in communication with each other, or how far they are placed. It is exactly like your NMR, but it is specific to a particular magnetic nucleus, and we are going to map that molecule and where these magnetic metal ions are going to be embedded in the structure. So that is the real purpose of doing nuclear quadrupole resonance. If you want to determine the bond lengths and the bond angles uh, of a molecule, if the molecule is present in the gaseous state, then we are going to make use of infrared and Raman microwave spectroscopy, electron diffraction. And if it is the liquid or solution, then we are going to make use of a spectroscopy called as EXAFS. What is EXAFS? Extended X-ray Absorption Fine Structure Analysis. EXAFS is extended, X-ray Absorption Fine Structure Analysis. Okay, and we also use LC-NMR. And for if it is a solid, there is no other way. If you want to find out the bond lengths and bond angles, you have to make use of single crystal X-ray diffraction and neutron diffraction. Okay. If you want to understand the electronic structure of a molecule, if it is in the gaseous form, you use UV visible spectroscopy, you use ultraviolet photoelectron spectroscopy, you use electron spin resonance, or in sometimes we call it as a EPR. So this is also a very interesting technique which people are not extensively using it to elucidate the structure, but one has to use it to elucidate the structure of a molecule. And if your sample, your molecule, is present in a liquid or a solution form, we use UV visible spectroscopy to study the electronic structure, as you must be teaching your students pi star transition, sigma star transition that are present in the organic molecules. They all occur in the UV region or visible region, whatever the spectroscopy that you are going to find out. So electronic structure is going to be revealed by UV visible spectroscopy for a liquid. And you can also do electron spin resonance of a liquid, and you can also do X-ray photoelectron spectroscopy if it is a liquid, because X-ray photoelectron spectroscopy is a surface technique. So if your sample is a liquid, you can just put a drop or a 2 drop to make sure that on a particular substrate, you put a couple of drops and then dry it, and then you can analyze it, the X-ray photoelectron spectroscopy. If it is a solid, if you want to understand the electronic structure, as you see, the things are becoming more or less simple when you are dealing with a gas and a liquid, meaning with the use of only few techniques, spectroscopy techniques, you can determine the structure of the molecule more or less, But the moment you go to the solid, you have to have a variety of techniques, large number of techniques to tell only one information. So that is also one of the difficulties, or one of the apprehensions a lot of researchers are having, why we have to work with the solids, because if you want to tell, or if you want to understand the molecule completely, for example, fingerprinting, groups present, molecular symmetry, bond lengths and bond angles, electronic structure, you need, as you see in this table, for solid, there are huge number of lists which I have listed, huge number of techniques which I have listed. And therefore, they say that, okay, with the help of minimum techniques, I'm able to get some idea. And therefore, they prefer to work on gas or a liquid or a, solution-based compounds, basically organic chemistry. So, if you want to understand the electronic structure of the solids, then UV visible spectroscopy is there. That means you can do the diffuse reflectance of your molecule in the solid form, and you can study the transitions that are present in that. You can study the optical band gap that is being present in the molecule. Lot of things you can do. Ultraviolet photo electron spectroscopy, UPS, you can do. X-ray photo electron spectroscopy, XPS, you can do. Mass wire, you can do. NQR, you can do. And single crystal X-ray and neutron diffraction. So all these techniques are going to give rise to the electronic structure of the solid. Okay, let us look at, see, as a scientist, we have not left any of the any part of the electromagnetic radiation for the analytical use. We are making use of all the entire spectrum from the electromagnetic radiation, entire things that we use it for analyzing a molecule or for other analytical purpose. So nuclear energies are present in the left-hand side, and chemical energies which are following that, and molecular energies are there, and then spin energies are there. So depending upon the energy, we select a particular technique. Depending upon the energies that are involved, or depending upon the energies that you will you will anticipate in your molecule, you will select a technique to understand its structure. So there are many things which are, electronic spectroscopy, rotational spectroscopy, vibrational spectroscopy, and then XRF, that is X-ray fluorescence, and then Mossbauer, XPS, UPS, ESR, NMR, NQR, electron diffraction, and X-ray diffraction. All these things are all associated with the energies, the spectral range. This slide gives you almost all in the form of energies, in the form of wavelengths, in the form of um, their utility also. And what are the time scales associated with these, some of the spectroscopy techniques I have listed in this slide. Suppose if you are doing NMR of a molecule in a solution, the energy of the excited state in hertz is 10 to the power 8. Typical relaxation time is 10 seconds. Typical line width is 10 to the power minus 1. Okay. And if you do ESR, the energy of the excited state is 10 to the power 10 hertz. I've just arranged it in the increasing order of energy, excited state energy level. And the typical relaxation time in seconds is 10 to the power minus 5. So you can imagine, it relaxes very fast. And typical line width is 10 to the power 5. And rotational spectroscopy, which is majorly used for gases to understand the structure of gases. So energy of the excited state is 10 to the power 11, and typical relaxation time is 10 to the power minus 4 seconds. And the typical line width is 10 to the power 4. Spectroscopy of the vibrational spectroscopy, if you want to do in gas, then energy of the excited state is 10 to the power 14. Typical relaxation is 10 to the power minus 8 seconds, and typical line width is 10 to the power 8. See, if you see very carefully, the relaxation and the typical line width in hertz, which are present in seconds, typical relaxation time and the hertz, they are almost inverse. 10, 10 to the power minus 1, 10 to the power minus 5, 10 to the power 5, like that. So electronic spectroscopy in solution, the energy of the excited state is 10 to the power 16, and typical relaxation time in seconds is 10 to the power minus 15, and typical line width is 10 to the power 15. Mass wire of the solid, if you want to do, energy of the excited state is 10 to the power 19, typical relaxation is 10 to the power minus 8, line width is 10 to the power 8. Okay, so we will just look into this. I mean, there is a ground state of the molecule, and you are pumping some energy to it, and depending upon the energy, it can go to the excited state. But before going into the excited state, that is the electronic transition, you are also having some vibrational transition, and you are also having some rotational transition. So the energy that you are giving, totally absorbed energy, is equal to energy electronic plus energy vibration plus rotation plus translation. Okay, this is what we teach the students, and the population distribution is the n upper divided by the n lower is exponential of minus delta E by kT. K is 1.381 into 10 to the power minus 23 joules per Kelvin. And for radiation, E is equal to h nu, that we know that, and hc by lambda. And I have just given you some conversion factors here. 1 nanometer is 10 to the power minus 9 meter. 1 centimeter inverse is approximately 11.98 joules per mole, which is 2.86 calories per mole. So I have just played around the different units in this slide so that you get an idea that whatever we are talking about is nothing but the energy scales. Whether it is centimeter, nanometer, or electron volt, everything is in the energy scales. Okay, now let us go back to the symmetry aspect, and we will again analyze it. So symmetry operations, as I told you that, and what is the point group for PtCl4 2 minus? This everybody knows, or if you ask the students, they will be able to tell that it is a planar molecule, and therefore it is a D4H symmetry, and its symmetry elements are C4, C2, I, sigma H, sigma B, sigma D, S4. Why I particularly chose this molecule is that you have all the symmetry elements that are present in this. E is there, principal axis C4 is there, secondary axis C2 is there, I is there, point of inversion is there, sigma H is there, sigma B is there, sigma D is there, S4 is also there. So almost all symmetry elements are present in this molecule. And how we can make use of this symmetry in spectroscopy? Let us apply symmetry to molecules in order to predict their behavior when exposed to electromagnetic radiation, which generates what we call as a spectrum. Okay, so what we do, we just shine electromagnetic radiation on a particular molecule, and we record how it is responding to that, and that is nothing but a spectrum. So by doing so, the interpretation and prediction of various spectra, especially let us consider proton NMR, becomes much simpler. It is quite easy for us to interpret it, and we are able to guess that this could be the arrangement of the molecule. When organic compounds interact with electromagnetic radiation, the energy absorbed is dependent on the structural environment in each molecule. So the energy, how the molecule is arranged, it depends on that, how much energy it will absorb. For example, different frequencies of infrared energy are absorbed by covalent bonds in different functional groups. You must be knowing the difference between a covalent and ionic bond. Covalent bonds is the pi bonds that we keep adding. So sigma, in addition to the sigma, we keep adding the pi, and therefore it is the covalent bonds. So carbonyls, carbonyl, it is a C double bond O. Carbonyls differs from alcohols, which also differ from alkenes. Okay, and if all groups and structures on a molecule absorb the same energy, spectroscopy would be a useless technique as an analytical tool, right? If they are all going to absorb the same energy, then you don't get any differentiation. Therefore, if on a molecule two or more structures are found to be in identical structural environments or symmetrical to another group, they will absorb EMR, electromagnetic energy, at exactly the same frequency. Each time a molecule absorbs electromagnetic radiation at a specific frequency, the instrument being used reports a single signal or a peak on a spectrum. For example, let us take the example of a infrared spectrum of the following molecule. Okay, we will observe distinct signals at different energies for the alkene. Alkene is a C double bond C. The alcohol, COH, OH is the alcohol, and the carboxylic acid functionality is found on the structure. Even though all these three units are present in the same molecule, but they are going to absorb the infrared radiation at different frequencies, and they are going to give us a different signal, and that is what I have highlighted in this. And this is nothing but the salicylic acid. This is nothing but the salicylic acid. In salicylic acid, you do see C double bond C, you do see alcohol, OH, and you do see acid COOH. Let us go a little deeper into this symmetry in proton NMR. I have taken a molecule. I always try to teach the students in a way that I keep asking them questions. We have to ask right set of questions for which we should always try to seek a right set of answers. That is how we can increase the curiosity among the students, especially the science students. So, what is the question that we can raise as far as this molecule is concerned? Just have a look at the molecule. Now, looking at the symmetry of proton NMR spectroscopy, a hydrogen based spectroscopy, do the two groups of hydrogens, we have marked it as HA and HB, absorb at the same energy to one another, is the hydrogens on the carboxylic acid groups similar to that? And another question, do the hydrogens on the methylene groups absorb at the same energy as the hydrogens on the acid? So, what would be the answer? To fully answer these questions, we must apply very simple symmetry rules to the molecule. What is the rule number one? Groups on a molecule that are determined to be symmetrically equivalent to one another behave spectroscopically also equivalent to one another. In other words, if two or more identical features on a molecule can be shown to be identical structural environments, symmetrically equivalent to one another, then they absorb energy at the same frequency and they produce one signal together in a spectrum. Next question we can raise to ourselves, are the methylene hydrogen atoms, HAs versus HBs, symmetrically equivalent to one another? And the acid group hydrogen atoms. Okay, the answer for both the question is yes and yes. And let us raise more question. How many signals or peaks do we expect from the methylene group hydrogen atoms and the acid group hydrogen atom? The answers are 1 and 1. The methylene group hydrogens on this molecule are said to belong to the same equivalent group, and therefore, according to rule number 1, they behave spectroscopically identically to one another, absorbing energy at the same frequency, one signal on a spectrum. A similar assertion can be made for the acid group hydrogen atoms. As human beings, we easily perceive when either objects are symmetrical or not symmetrical. So the example above is a very good example to analyze using symmetry, and we can easily assert that we have two sets of protons, that is acid hydrogens and methylene hydrogens of symmetrically equivalent hydrogen atoms, which gives two different signals in a spectrum. With more complex molecules, it might be difficult or impossible to see this symmetry. Therefore, we need a foolproof method for detecting its presence. Look at the following molecule. Just have a look at the molecule and raise a question to yourself. Are the acid hydrogen atoms symmetrically equivalent to one another now? Or the alkyl hydrogen atoms, HAs versus HBs? The answer is no. The symmetry of this molecule has somehow been broken, making the hydrogen atoms on the alkyl groups and on the acid groups to be in a single environment, slightly different environments from one another. And therefore, next question which you can raise to yourself, how many signals do we expect from alkyl hydrogen atoms and the acid groups? The answer is you will observe three signals and alkyl hydrogen atoms and two from the acid groups. Since none of the alkyl hydrogen atoms belong to the same symmetry equivalent set, each will absorb at a unique frequency and give a unique individual signal. So the energies at which they absorb might be very close to one another, but still they will be different. So, what set of formal rules can be applied to molecules in order to determine whether groups are symmetrically equivalent or not? Let's return to our original molecule. You just look at that molecule. If I ask you to close your eyes, then if I rotate this molecule 180 degrees about an axis in the plane of the board and through the central carbon of the molecule, if I then had you reopen your eyes, would you be able to detect that I rotated the molecule? This is a question that I am asking. The answer is no. The axis is the rotational axis of symmetry, and because of this rotation, they transform, one half is transformed to the another half, and therefore they belong to the same symmetry equivalent set or groups. Okay. So the actual process of rotating the molecule is the symmetry operation, as we learned earlier. As the hydrogen atoms on the alkyl groups or the acid groups exactly change their position, they are said to be exactly transformed into one another. What is the rule number 2, which we can certainly make use of? Groups on a molecule that transform exactly into one another during a symmetry operation are symmetrically equivalent to one another and therefore absorb energy at the same frequency. So they belong to the same equivalent set and give one signal or a peak on a spectrum. Now look at this molecule very carefully and ask yourself a question. Are the two hydrogen atoms on either alkyl group symmetrically equivalent to one another, Ha versus Ha prime or Hb versus Hb prime? To show that the two hydrogen atoms on each alkyl group are indeed equivalent, we utilize a second different symmetry element found on the molecule. Can you find it? Yes, it is called as the internal plane of symmetry or the mirror plane, and it is, as I told you earlier, it is given the symbol sigma. With the reflective plane of symmetry, one half of the molecule is completely and exactly reflected into the other half, second half. The two halves of the molecules are the mirror images. And so there is an internal mirror or plane of symmetry, and each group on the right half of the molecule is exactly reflected into the each group on the left half. The presence of this plane of symmetry along with the axis of rotation shows that the alkyl hydrogen atoms are all equivalent to one another. That means you have to look at the symmetry operations and the presence of symmetry elements that are existing in the molecule before even trying to go and then start interpreting the proton NMR spectrum. Let us return to our molecule, which we found to be non-symmetrical. So let us raise a question. Do any of the hydrogen atoms in this structure belong to the same symmetry equivalent set? And to answer this question, what you are supposed to do? You have to simply identify any symmetry element which may be present in this that can cause the groups to transform into one another. Suppose, are there any legitimate symmetry elements in this molecule? The answer is no. There are no legitimate symmetry elements. There is no symmetry element nor any symmetry operation that can be performed on this molecule to transform any of the atoms in the structure. See, initially we said a molecule containing different environments, you get different signals. Then we look into the entire molecule and whether one half can be replaced with the other half. Now we are saying one half cannot be replaced with the other half. That means, is there any legitimate symmetry elements in this molecule? No. There is no symmetry element nor any symmetry operation. And therefore, all of the 5 hydrogen atoms belong to 5 separate sets, and therefore they give 5 distinct signals on a proton NMR spectrum. So you can see the influence of symmetry on the results that you get on the proton NMR spectrum. Rule number 3, in order to show that any two or more groups on a molecule are symmetrically equivalent, only one symmetry element that is exactly transforms the groups need to be found on the molecule. So, question is how many unique symmetry equivalent sets of hydrogen atoms are on the following molecule? How many different signals will they generate? Again, to answer this question, you must first identify symmetry elements, any one of them is there or transformed or not. So, is there a symmetry axis of rotation in this molecule? No. And is there a plane of symmetry? No. How many different signals are expected from the hydrogen atoms? 6, because there are 6 different. And so the less symmetry. So I am stopping my second uh, segment with this note: the less symmetry found on a molecule, the greater the number of different signals will be found on its spectrum. So the lesser the symmetry, more number of signals. Higher the symmetry, less number of signals. So with this, I'm stopping my second segment. We will further discuss in the third segment.